We're about to dive into a story about a massive system meltdown, and it all comes down to a single, simple command. This is about a deep, often misunderstood truth about Node.js and how what you think is happening when you run your code can be dangerously different from reality. So, picture this. It's the middle of the night. A huge fintech platform is running smoothly until suddenly, it's not. A critical service, the one that handles payment webhooks, just starts to fall apart. And for the on-call engineer, that's the page that means your night is officially over. Okay, so what's the first symptom? It's bad. I mean, really bad. Requests that should be basically instant, less than 200 milliseconds, are now taking 30,000 milliseconds. That's 30 full seconds for a single request. The whole platform is just grinding to a halt. And at the same time, the servers are just screaming. CPU utilization is pinned at 98% across the board. The machines are running as hot as they possibly can, but for some reason, they're not actually getting anything done. And this is where it gets really weird. The engineer dives into the logs, nothing. Checks the database for slow queries, nothing. External services, all fine. The system is clearly dying, but all the usual suspects have an alibi. It's like trying to find a ghost in the machine. So the hunt begins. The team starts going down the list, checking all the standard things that could cause a failure like this. But as you're about to see, they were looking in all the wrong places. I mean, they ran the whole checklist. Application logs, clean. Database, happy as can be. External APIs, responding super fast. They even checked the event loop lag right before the incident, and it was perfectly healthy. It was just dead end after dead end after dead end. And here's the big reveal. The reason they couldn't see the problem is because it wasn't in their application code. It was happening one level deeper, at the runtime level. All their monitoring tools were looking at the tip of the iceberg, completely blind to the enormous problem happening right underneath the surface, inside the Node.js engine itself. After hours of chasing these ghosts, the whole investigation takes a sharp turn. The team finally realizes the issue isn't what the app is doing while it's running, it's the massive, hidden cost of just getting it started. And boom, there it is, the cumulative startup cost. See, their system was designed to auto-scale. When traffic spikes, it just spins up new instances. But here's the catch they missed. Every single time a Node.js process starts, there's this huge initial burst of CPU usage. And when dozens of these happen at the exact same time, that cumulative cost acts like a shockwave, knocking the entire system over. This chart shows the absolutely brutal feedback loop they were stuck in. You get a traffic spike, so the system tries to help by spawning new pods. But those new pods immediately cause a massive CPU spike just by starting up. The autoscaler sees this crazy high CPU and thinks, oh man, we're still overloaded. We need even more pods, which of course just makes the whole thing worse. It's a death spiral they created themselves. So to really understand why this happens, we need to pop the hood. Let's dig into what Node is actually doing in those first few hundred milliseconds, way before a single line of your own code gets to run. So it turns out Node has this really rigid three-step startup process. First, it creates something called a V8 isolate. Then it resolves the module graph, and finally, it initializes the event loop. The key thing to understand here is that all three of these are synchronous and blocking. The entire world stops until they're finished. First up, V8 isolate creation. Think of this like building a brand new, completely isolated factory just to run your code. It has to set aside memory for the heap, warm up the compiler, the whole shebang. And on a cold start, this alone can eat up 50 to 150 milliseconds of pure CPU time. Okay, the factory is built. Next, Node has to figure out what to do with your code. It has to find, parse, and execute every single module you've required. For a modern app, this can mean thousands of file system calls. And again, it does this synchronously. It's just one after another. A massive blocking operation. And finally, the last step. It has to initialize the event loop. This is where it sets up the powerhouse C library called Libuv, the thing that handles all the async I/O that makes Node so great. Only after all of that heavy lifting is done can your app actually open for business and start handling requests. So you might be sitting there thinking, well, why is it designed to be so rigid? And that's a fair question. It's not a flaw, though. It's a fundamental requirement. Because JavaScript is single-threaded, the entire environment has to be loaded in a very specific, deterministic order to guarantee that your code runs predictably every single time. Okay, so we've diagnosed the disease. What's the cure? The answer, it turns out, isn't just to optimize your startup. It's about thinking differently and understanding the trade-offs you have to make when you're scaling. Let's get into it. And this table breaks it down perfectly. You've got 3 basic paths. 1, you can optimize your startup code. That helps, but you can never get rid of that core Node.js startup cost. 2, you can keep a warm pool of instances running and ready to go. You get instant capacity, but you're paying for resources you're not always using. Or 3, you can shift to fewer long-lived processes. This actually aligns way better with Node's design, but the blast radius is bigger if something goes wrong. See? No magic bullet, just trade-offs. And this quote just hits the nail on the head. The most intuitive, simple solution, hey, things are slow, let's just add more servers, is the very thing that makes the problem worse. It's like throwing gasoline on a fire. So the real solution is a change in mindset. You have to design your systems to work with the Node runtime, not fight against it. That means you design to minimize process churn. You make sure your health checks are smart enough to know when an instance is truly ready to handle traffic. And you start monitoring the runtime itself, the V8 heap, garbage collection, not just your application's output. All right, let's pull back for the big final lesson here. Because this isn't just some interesting technical puzzle. This is about a fundamental conflict that has massive, real-world consequences. And when I say real-world consequences, I mean cold, hard cash. During that 1 week of these scaling incidents, the team burned through 340% of their monthly infrastructure budget. Let that sink in. This isn't just an engineering problem, it's a financial one. And this is the core lesson of the entire explainer. You can have brilliant engineers writing perfect code, but production systems often fail because the architecture is fundamentally at odds with how the runtime actually operates. If your architecture is fighting the very nature of its foundation, it's not a question of if it will fail, but when. So I'll leave you with this one question to think about. Take a hard look at your own systems, your own scaling strategies. Are they designed in harmony with how your runtime really works? Or are you, right now, unknowingly, setting the stage for your own 2:47 a.m. wake-up call?